Hey again, it's Mr. Lum. We're going to be doing some more Chemistry 11 and some more significant figures. And this time we're going to look at significant figures and how we can use them in our measuring devices. So what we have here is a picture of a graduated cylinder and a ruler. So before we get started, let's do a little review on significant figures. So sig figs are made up of certain digits or numbers that we are certain about and one, or I'll put that in blue, one uncertain digit. So keeping that in mind, let's take a look at this first one right here. So first off, what are we certain about? We are certain that the amount of water in here, and remember when you're measuring in a graduated cylinder, you measure from the bottom of this line right here, or as we call the bottom of the meniscus right here. So we are certain that this is greater than 61, 62, 63. We're certain that it's greater than 63 milliliters. Okay, let's pretend these things are measuring in milliliters right here. Okay, we are also certain that it is less than 64 milliliters. Now, for our last number, our uncertain, remember it's all the certain numbers plus the one uncertain number, is somewhere in between here. And we don't know exactly whereabouts it lies in between these two lines. But to me, that looks about 5/10, about halfway. So I'm going to take half of this. I usually, instead of rather than writing 1 over 2, I usually put this in tenths. So it looks to be about 5/10, and I'm going to multiply that by the amount of one division, and one division right here is 1 milliliter, and that's just simply 0.5 milliliters. I then take this number and I add it to this number, our lowest number. So 63 plus 0.5 is 63.5 milliliters. Okay, and that seems to be about our volume right here. Now, let's take a look at our ruler right here. So here it is, our object reaches a length of right about to there, and we see that it's definitely going to be greater than this subdivision and less than this subdivision right here. So again, we're going to do the exact same layout and write down what are we certain about. So we're certain that it is greater than, now let's figure out what it is here. So unlike this one, which has between 60 and 70, each one is going up by 1 milliliter. This one only has 4 in between here, so it's going to be going 82, 84, 86, 88, and then 90. So we are certain that it is greater than 86 centimeters. We are certain it is less than 88 centimeters. Now here, it seems to be, now I'm uncertain about this, but it seems to be about 8/10. Maybe someone could argue that it looks like 7/10. But to me, it looks like it's about 8/10. So 8 over 10. So I'm uncertain about this, but it looks to me that it's about 8/10 of this subdivision right here. And so I'm going to multiply that by the length of this one subdivision, which happens to be 2 centimeters. So 8 over 10 times 2 is equal to 1.6 centimeters. I do the exact same thing. I take my lowest number, which happens to be 86, and I add it to this one, so 86 plus 1.6 is going to be 87.6 centimeters. Okay, and that is my length of this object that reaches to right here. Okay, so that's going to bring us to our next topic, and this will be just a quick one, and it's just going to be the differences between precision and accuracy. So in English, these two words mean pretty much the exact same thing, but in science they have different meanings. So accuracy is the agreement between experiment data and a known value, and precision is how well the experimental value agrees with each other. So here is a diagram of this, and what you can think of is the target, so the blue, red, and yellow portions of the target. You can think of that as the known value. Okay, and here are each one of these x's you can think of as the experimental value. So for this first one right here, what we can see is that the experimental values, or the x's, are agreeing with the known value. So yellow is the bullseye, or yellow is the what we believe is to be the correct, in some ways, value. And we can see that the experimental value is the same as the known value, so the x's are on the yellow. So this, in this picture right here, it is both precise and it is accurate. It is accurate because all these x's are on the yellow. It is precise because all these x's are pretty much on top of all the other x's. So the x's are agreeing with each other, and therefore it is precise. They're hitting roughly the same place. It is accurate because the if I was to take the average of all these x's, it is hitting the bullseye. Now here is something where if I took the average of all these x's, it's not hitting this bullseye right here. It's hitting just a little bit off from it. So this is not accurate. As we see right here, it's not accurate. However, it's still precise because all of these experimental values are agreeing with each other. All these x's are on top of each other right here. So it is precise, but it's not accurate. Now, again, let's take this look at this next one. If I were to take the average of all of these experimental data, it would be somewhere in this yellow. So therefore, it is accurate. However, these x's are not on top of each other, so it's not that precise. Okay, it is accurate, but not precise. Now this one is neither. It's not accurate. If I took an average of this, it is not in the bullseye. And it is not precise because the experimental data is not exactly agreeing with each other. The x's are not on top of each other. So what I want you to do, and what we're going to discuss in class, is I want you to come up with some real-world applications where something is precise and accurate, neither precise nor accurate, and something that's precise and inaccurate, and accurate but not precise. Okay, so think of and research on the internet, and we'll discuss it in class, some real-life scenarios where these four will be present.